What is voltage? What is current? Why does it matter to you and your project? And why am I standing in front of a beerette for a video based on electricity? All this in this episode. So in this example, what we can see is I have my beerette with fluid in it. I think we can all agree that that column of fluid is creating some pressure. That pressure is coming from the force of gravity. Why are we using fluid in a beerette for this example? Well, we can't see electrons in a battery. We can't see the chemical reaction taking place in the battery. So this gives us a visual, and it's a visual I've used with a lot of students that I've taught this concept to. So in this column, we have pressure. In an electrical system, we call that pressure voltage. Voltage is the terminology used for electrical pressure or electrical potential. This column of fluid is giving us a potential. When we talk about current, which is measured in amps, what we are talking about is the actual flow of electrons through the circuit. In this example, our flow is represented by our fluid. Currently, there is no flow taking place in my system. The reason there's no flow taking place is because I have an infinite amount of resistance. This circuit is completely blocked by my valve. How do I create a flow of current? Well, I have to open my valve. What happens when I open my valve? I'm creating a decrease in the amount of resistance, similar to what happens when I turn on a switch. As I open my valve, we start to see a flow of current into my secondary cylinder. That flow of current represents the flow of current through a wire, which would be measured in amps. There's two things that affect this flow of current: my voltage and my resistance. If I increase my pressure, well, how would I increase my pressure here? I would increase it by putting more fluid in here, or by raising the level of it. How do I increase my voltage in a battery or my pressure in a battery? By increasing the electrical charge. Increasing pressure will increase current flow to a point, provided whatever that current is flowing through is able to support that flow of current. This is where we do have to draw a little bit of a distinction between a pipe with fluid going through it and an electrical wire. We know that electrical wires are not hollow. We know that they're made out of copper. And there's a property that takes place that does not happen in this hose. We'll get into that a little bit more later in the video. But in general, increasing resistance will decrease current flow. And when I refer to resistance in an electrical circuit, and we're going to focus just on one electrical circuit today, we're going to focus on a fan circuit. When I talk about resistance in that circuit, I'm talking about the total resistance throughout the entire leg of that circuit. And that's the resistance from the time the current leaves the battery and travels to my fuse, if it's a fuse circuit, from my fuse to my switch, through my switch, from my switch through the wire to the fan motor, through the windings of the fan motor, to my chassis ground, if it's a chassis grounded component, through my chassis, the metal of my chassis, from my chassis ground, or from my battery ground, I should say, through the cable up into the battery and back to the return to the source. That total resistance in that loop will impact my current flow through the circuit. Now, that resistance does not necessarily remain constant. To show you an example of this, I'm going to allow my fluid to flow again, and I'm going to raise this tube. As I raise this tube and the levels become similar, we see the flow of current decrease greatly. Why is that happening? Well, that's happening because I'm creating a potential in my secondary tube that's acting in the opposite direction. The same thing happens when your electric fan motor starts to spin. Most of us are familiar with the fact, and if you're not, I can do another video on that, with the fact that a motor, a DC motor, operates by using a magnetic field. And we know that as we pass electricity through a wire, we generate a magnetic field. That magnetic field is what allows our motor, our fan motor, to spin. Conversely, we know that as that fan motor is spinning, it's also creating an electrical potential, but it's creating an electrical potential in the opposite direction. Call that counter electromotive force. And that is actually a benefit to us at times, because what that does is it controls the current going to that fan motor. If we didn't have counter electromotive force, what would happen is we would have an excessive flow of current to that fan motor. Eventually, what would happen is our wiring would heat up, our resistance would become higher due to the hot wiring, and we would actually see a decrease in speed of that fan motor. Okay, now we're going to apply what we've just talked about to an actual electrical system on a race car. And we're going to focus specifically on one circuit, the fan circuit. My reason for choosing the fan circuit is that this is one of the highest draw continuous running circuits on the car. Aside from your ignition system, which can be comparable and is a little bit harder to demonstrate, although I can do a video and demonstrate that at some point down the road, the fan draws probably the most current continuously of any of our other components on the vehicle. So we're going to focus on the fan motor. Right now you can see that our battery voltage is approximately 16 volts. When I turn this fan on, what you're going to see happen is you're going to see a drop take place in that voltage. Right now there are no switches turned on. It's the equivalent of having the fluid in the tube with the valve turned off completely. Once I turn that valve on, or once I close that switch and I allow for current flow, we see a drop in that pressure. In the case of the tube, it was because our fluid started to drop. In the case of our battery, it's because current is now flowing from the battery to our fan. We're also going to see that that voltage is going to drop significantly, then increase a little bit, and then notice when I shut the fan off that we're going to see a slightly lower voltage than we started with, which will gradually recover back up to close to our initial voltage. So I'm going to go ahead and click my fan on. And we saw that initial drop down to about 14.8, back up to about 15 volts. So we're seeing about a 1 volt drop right now. Once I shut that fan off, I see I recover up to about 15.7, 15.8, and this will eventually recover back up to about 16 volts again. To take this a step further, I want to demonstrate this looking at both the voltage as well as the current flow, and we're going to do that using a lab scope. Now I know not everyone has used a lab scope before, but most of you have probably used a voltmeter at some point, a digital voltmeter. A lab scope does the same thing, except what it allows me to be able to do is to look at multiple channels at the same time, and also to be able to graph the changes on my screen and see those changes over a period of time. Whereas a voltmeter will just take an average depending on the sample rate. So what we're going to do is I'm going to take you through my setup here. Channel 1 is connected directly to my battery and is being displayed as my yellow trace going across my screen. Each of the dotted lines on my screens horizontally represents 5 volts, so my battery is reading approximately 16 volts at this point. Remember, there's no switches turned on, so there's a minimal amount of current flow, and therefore I'm reading full battery voltage. My second channel is going to measure the current flow from my battery. Now we can't measure current flow directly because remember, current flow is a measurement of the flow of electrons. So what we do instead is we measure indirectly using a current clamp. A current clamp takes advantage of a property that we talked about earlier, that as electricity moves through a wire, it generates a magnetic field around that wire. What my current clamp does, uses that magnetic field and produces a voltage relative to that magnetic field that can then be displayed on my screen. Right now my setting is 1 millivolt, representing every 100 milliamps of current flow. The numbers don't really matter because we're not looking to take a perfect measurement of current flow. All we're looking to do is to be able to see that change take place when I close that switch and the fan turns on. So right now, if we look at our screen, we are seeing a reading of approximately 16 volts. So what's going to happen when that fan turns on? Well, as we know, we are going to see our voltage drop, and we're also going to slightly, and we're also going to see our current increase, because current is now being drawn, kind of like turning the valve on. Let's watch what happens, and let's talk about why this happens in the way that it does. Okay, so here's my capture of my current in blue and my voltage drop in yellow. Now, a couple of important things happen here that I want to point out to you. Notice that when I initially turn my fan on, I see a giant spike in the current. You will see this with any DC electric motor. We call that the inrush current. What's happening at that point is the equivalent of when I was holding my test tube down low at the same time that I was turning my valve on, and we saw a very fast flow of current into my secondary tube. Remember that once this motor starts to run, two things are happening to increase the total resistance. One, the wiring between the battery and the fan motor, and from the fan motor back to the battery, is increasing slightly in temperature. When you increase the temperature of copper, its resistance goes up. Copper is what's called a PTC, or a positive temperature coefficient resistor. So as that wiring, and that includes the windings of my electric motor, as that heats up, its temperature increases, and therefore my resistance increases slightly. Part of the reason we see this drop in current taking place. In addition to that, as our motor starts to rotate, it's generating electrical potential in the opposite direction. Which is why what we are seeing is the current very quickly drop off as the electric motor starts to generate potential opposite direction. Equivalent to me holding the secondary tube higher in our liquid example. Eventually this balances out, and you can see that our graph becomes very jagged on that blue line. The reason that graph is becoming jagged is we have to think about how an electric motor works. Inside this electric motor we have a commutator, which is a switching device. And it's switching current on and off to different parts of the electric motor as the brushes come into contact with that part of the commutator. And that's where those bumps come in. We can actually study an awful lot that's beyond the scope of this video about electric motors looking at these graphs, including actually calculating the speed of our electric motor. Notice that our yellow line, our voltage, changes inversely to our current flow. Well, why is that happening? As current is flowing out of our battery, it is causing that drop in voltage to take place. So when our current spikes, we see a very high drop in voltage. As that counter-electric motor force starts to develop, and as that resistance from the copper heating up starts to increase, the current flow decreases, and we see the voltage start to increase back up to where it levels out. When we turn our electric motor off, we are stopping current flow to that electric motor. We're opening the circuit. And therefore we see our voltage go back up to our 16 volts. But notice what also happens at that turnoff point. Notice that we see current in the opposite direction. Well, the motor doesn't come to an instant stop. It coasts. And as this motor is coasting, what it's doing is producing current in the opposite direction. That electromotive force that we talked about, well, now that there's no potential towards the electric motor, what we have is voltage being generated by that electric motor in the opposite direction. And we see current flow happening because of that in the opposite direction. And that's why we see our negative line on our graph. Hopefully this helps you to better understand the concept of voltage and current. When we look at a question like 16 volt battery, 12 volt battery, what's the best way to go? Keep in mind that a healthy electrical system, including good solid connections, we talked about crimping in a previous video, including good solid grounds, And I know there's a lot of conversation out there about using chassis grounds versus grounding everything back to the battery. We can talk more about that in future videos. I'm not totally opposed to using chassis grounds, but the key to that is good chassis grounds. Be familiar with the components that you're wiring. Be familiar with the current that that component draws, and make sure that you are providing the proper path to and from that component for your electric current to flow. If you do all of that, a 12-volt battery will supply enough potential for most of the components on your car. A 16-volt battery gives you a safety net. And that's what I tell most people. That 16-volt battery is really a safety net. Hopefully you found this information helpful. Feel free to like, to subscribe, to make suggestions in the comments, and let me know what you'd like to see in future videos.